Welcome to the deep dive. Ever wondered how the incredibly complex systems delivering your electricity reliably, getting natural gas to your home, ensuring clean water flows, and even powering your internet are managed behind the scenes?
Yeah, it's pretty amazing when you think about it.
It really is. Today, we're plunging into the world of utility networks, the digital backbone that makes it all work.
Think of it as a highly intelligent blueprint.
Exactly. A blueprint for these vital services. Our mission in this deep dive is to unpack its core architecture, its management principles,
Yeah.
basically give you a clear understanding of how it functions without getting, totally bogged down.
Right, keep it focused on the key insights.
We'll explore the structure, the critical role of rules,
Oh yeah, rules are huge.
subnetworks terminals, tiers, and then network categories and attributes.
Ugh.
Okay, let's unpack this because here's where it gets really interesting.
Absolutely. And what's fascinating is just how sophisticated utilities are becoming in digitally mirroring these huge physical systems. Our sources really highlight the utility network as this central model, constantly managing the network topology.
So it's dynamic, not static.
Exactly. It's built on domain networks tailored for electric, gas, water, whatever the utility is. And underpinning all of that is the structure network.
The structure network, okay, so that's like the physical framework. The unsung hero.
You could say that.
We're talking poles, towers, trenches, vaults.
Yeah,
The stuff that doesn't carry the resource but holds it all up.
precisely. When you first set up a utility network, the system automatically generates this structure network.
Okay.
It comes with specific digital representations feature classes, they're called, like structure junction for, say, a pole,
Uh-huh.
structure line for a wire between poles, structure boundary for maybe a substation fence, and tables to hold the data.
Got it.
And it's vital to grasp that this is focused purely on the physical scaffolding, the stage, if you will.
The stage for the actual utility circuit.
That's it. So the system is cataloging every physical bit down to the type of pole or conduit material.
Wow, that detailed.
Oh, yeah. And that detail lets the domain networks accurately model how the electricity or water actually flows through that infrastructure.
Got it. So once that physical structure is mapped out digitally, then you add the domain networks, the ones that model the actual flow, electricity, gas, water.
That's precisely right. For each domain network you add, let's say, electric BIC, the system automatically creates its own set of building blocks.
Like what?
5 key feature classes. Device, like a transformer.
Okay.
Line, like a cable. Junction for connections, assembly for groups of things, and subnet line, which represents a traced subnetwork, plus supporting tables.
So it's layered. Structure first, then the specific utility domains on top.
Exactly. Foundational structure. Then the specific domain networks modeling the behavior of each service. It's quite elegant, really.
Okay, makes sense. So we have the components, digital versions of pipes, wires, transformers. But how does the system know what can connect to what, or what's a valid operation? That's where rules come in, right?
Absolutely. Rules are foundational. They're like built-in quality control.
The digital rule book.
Pretty much. Dictating how features can interact. This ensures the data reflects the real world, and makes operations way more efficient.
And there are two main kinds.
Yeah, 2 primary categories. Connectivity rules, governing how things link up,
Okay.
and attribute rules, which manage the data about those things.
Connectivity rules sounds pretty intuitive. What can connect to what? Like you can plug a lamp into an outlet, but not straight into a generator.
Exactly that kind of logic. They prevent impossible connections by defining the allowed relationships.
So if there's no rule,
It won't let you make the connection. Simple as that. Drastically cuts down errors, improves data integrity.
so how specific can these rules get? Are there different types of connections they manage?
There are 3 main types. First, junction edge connectivity.
Point to line.
You got it. A point feature, like a transformer, connecting to a line feature, like a distribution line.
Okay.
Our sources give a structural example. A structure junction, maybe where equipment mounts on a pole, connecting to a structure line, like a wire running between poles.
Okay.
It's about how equipment physically attaches.
Makes sense. And the second type.
Junction connectivity allows 2-point features to connect directly, often using terminals. We'll get to those.
Okay.
An example here. An electric device, maybe a fuse in a substation,
Right.
connecting directly to an electric junction, like a connection point on a bus bar. So equipment to equipment links at specific points.
Okay. And number 3.
Edge junction edge connectivity. This lets 2 lines, like cable segments, connect through an intermediate junction. A A splice, maybe.
Ah, okay.
The example is an electric line, say a bus bar, connecting to another electric line, a connector, via an electric junction, the actual connection point, defining valid paths through intermediary points.
Wow, that's incredibly detailed. How do you actually set these up in the system?
There's a specific tool, a geoprocessing tool called Add Network Rule.
Okay.
And interestingly, you have to temporarily disable the network topology to add or change these rules.
Oh, really? Why is that?
Ensures the changes are applied consistently across the board, like updating the core operating system.
Gotcha.
Once you've defined your rules, and you can get very specific based on asset groups, types, terminals, subtypes, feature classes.
Lots of options.
Yeah. Then you re-enable and validate the topology. It checks if everything still complies with new rules.
Like a system check after an update.
Exactly.
Okay, so connectivity rules handle the what connects to what. What about attribute rules? They manage the data about the features.
Precisely. Attribute rules automate populating fields, prevent invalid edits, and do automated QA/QC checks. Think of them as smart data assistants.
Smart assistants.
I like that. And utilities are increasingly using these proactively, like flagging assets with changing voltage levels before an outage.
Ah, predictive maintenance based on rules. Cool.
Yeah.
So the first type is calculation rules autofill smartly.
Yeah, that's a good way to put it. They handle lots of useful time-saving stuff, autofilling who created a feature or the date, assigning default values like phase code or voltage, calculating length or area automatically when you create or edit something.
Wow.
Triggered on insert and update actions. Saves tons of manual entry, ensures key data is always there.
Huge time saver and great for consistency. What about the stop wrong edits type constraint rules?
These are your gatekeepers, preventing bad data from getting in.
How so?
They can enforce mandatory fields, no leaving critical stuff blank. Ensure values are within realistic ranges voltage between 0 and 400, say.
Right.
Or even block edits based on status, like you can't modify something marked retired.
Ah, okay.
Again, triggered on insert and update, stops errors at the source.
And the last one, validation rules.
Yeah.
The QA/QC inspector.
These are your automated checks on existing data. They find errors or inconsistencies based on your criteria.
Like what kind of checks?
Checking if every substation has at least one feeder connected.
Okay.
Making sure asset IDs follow the right format. Identifying features missing key info, like a pole without a material type assigned.
And how are these triggered?
Usually by a batch tool that runs checks periodically, or sometimes even when you save edits, giving immediate feedback.
This whole rule system sounds absolutely vital for keeping the data clean and, well, usable.
It really is. Foundational for a functional utility network.
Okay, moving on then. Our outline mentions subnetworks. What are they exactly, and why are they significant?
A subnetwork is basically a logical group of connected features within a specific tier.
Okay, like a circuit.
Exactly, like an electric circuit from a substation to customers or a pressure zone in a water system. They're defined and managed by subnetwork controllers.
Controllers.
Yeah, so now that we have the validated components and rules, how do we group them into functional units? That's subnetwork.
Subnetwork controllers.
Yeah.
Sounds like they're the key. What do you need to set them up?
Few prerequisites. First, topology must be enabled and valid.
Right.
Each subnetwork needs a unique name across the whole utility network.
Unique name. Got it.
And the controller itself needs a unique name within its tier. Avoids confusion.
Makes sense.
And of course, the feature you pick as a controller has to be eligible right asset type, like a substation transformer for an electric feeder.
And what does the controller do, practically speaking?
It acts as the origin point, or sometimes the end point, the termination point for that subnetwork.
Okay.
It's crucial for management. Essentially defines how the resource, electricity, gas, water, flows in that section.
Our sources mentioned two types, source-based and sink-based. What's the difference?
Good question. A source-based controller means flow is mostly outward from that point.
Like a power station.
Exactly. Or a water treatment plant sending water out. Or that transformer feeding a distribution line.
Okay. And sink-based.
Flow is primarily inward. Think of a stormwater drain collecting water. Or the entry point to a wastewater treatment plant.
Got it. So once you've picked these controllers, how do you actually, make the subnetwork in the system?
Few steps. First, designate the feature as a controller. Often involves specifying a particular terminal on it, more on terminal soon. Then, validate the topology. The system checks if the new controller setup works with the rules and existing features.
Right, the system check again.
Then you run a specific geoprocessing tool, a command basically to update the subnetwork. It traces out from the controller, following the rules, and defines the subnetwork's extent.
Okay, so the controller often relies on a specific point, a terminal. Let's dive into those. What are terminals modeling?
Think of a terminal as a very specific connection point on a piece of equipment.
Like on a transformer or a valve.
Exactly, where power comes in and goes out of a transformer, or where gas flow is controlled on a valve or on a switch. In the digital model, they represent these physical entry and exit points.
So they're logical connection points, defining start and end points for traces.
Precisely. Crucial for defining where a subnetwork trace begins or ends within a device.
So one real-world device could have multiple terminals in the model.
Absolutely. Depend on complexity. Our sources give good examples. A simple electric switch might just have two, input and output. But something like a pump in a water system probably has at least suction and discharge terminals. For an electric switch, maybe terminal 1 is the source side, where power comes from.
And these aren't just generic points, right? They have properties.
Yes, definitely. Key property is directionality is flow only one way, directional, or either way, bidirectional. Then there's upstream, downstream designation, and crucially, valid paths.
Valid paths.
These define the allowed internal connections between terminals on the same device. Each path gets a name, like bypass active, and a value the system uses.
So you're modeling the internal workings too. How do you set these up?
There's a tool for that, set terminal configuration.
Naturally.
And just like with rules, you need to disable the topology temporarily while you configure these.
Okay, disable topology again. Got it.
Ensures changes apply correctly. And usually you need to be the network owner in an enterprise setup to do this.
Right, permissions.
By default, the system assumes just one terminal unless you configure more.
The bypass switch example in the sources sounds helpful here. Can you walk through that?
Sure. A bypass switch lets you either include a main device, like a regulator, in the circuit, or bypass it for maintenance.
Right.
This example switch has 4 terminals. Now, mathematically, there are 6 possible paths between 4 points, right? But the terminal configuration defines only the valid, operationally meaningful paths.
Okay.
So one valid path might just connect terminal 1 to 2. That effectively isolates the main device.
Bypasses it.
Exactly. Another configuration might define 2 paths simultaneously, 1 to 3 and 4 to 2. That energizes the main device, puts it in circuit.
Ah, I see. So the valid paths control the device's state in the model.
Precisely. Shows how defining these paths lets the model accurately represent complex operations.
That makes terminals much clearer. Very practical. Okay, let's shift to how these subnetworks are organized using tiers. What's a tier?
A tier is basically a logical group of subnetworks that all follow the same rules and settings. You set these up early on when you first add a domain network, like electric or water.
Right.
And how you define tiers leads to 2 main types of domain networks, partitioned and hierarchical, different levels of organization.
Partitioned and hierarchical. What's the main difference there?
With partitioned, often used for electric, telecom flow is usually step-by-step through tiers, and a feature belongs to only one tier at a time.
Only one tier.
Yeah, but it could be in multiple subnetworks within that single tier. Think linear flow. High voltage transmission tier, then subtransmission, then distribution. Defined order, defined flow direction.
Okay, and hierarchical. Used more for gas or water.
Yes. Hierarchical allows more complex layered structures. A single feature can belong to multiple types of subnetworks across different levels, different tiers.
Simultaneously?
Exactly. So a water main could be in a high pressure zone subnetwork, one tier, and an isolation valve zone subnetwork, another tier. Very flexible for modeling overlapping functions.
Got it. And there's a tool for adding tiers and tier groups too.
Yep, a geoprocessing tool. Highly configurable when you first set up the network.
Okay. Now, network categories, what's their main job?
Network categories are essentially labels, descriptive labels you apply to assets based on their asset group and type.
Like tags.
Yeah, like specialized tags identifying specific roles or characteristics. The system provides a few defaults.
Such as?
Subnetwork Controller, which we talked about, helps identify those key features. Also, Subnetwork Tap, attribute substitution, each has a specific system function.
So these tags let you easily find and work with specific types of assets.
Exactly, and they're useful for analysis. There's even a trace by network category function.
Oh, interesting.
Lets you trace only features with a specific category assigned. Makes targeted analysis easier.
Makes sense. Finally, Network attributes, how do they fit in?
Network attributes are values pulled directly from your feature class fields.
Like pipe diameter
Yeah,
or voltage rating.
exactly. Pipe diameter, wire voltage, valve status. These values get stored and indexed right in the network topology. And they update automatically when you validate the topology after making data changes. Makes them fast to access for analysis, especially tracing.
Can you give that pipe diameter example again, how it works in a trace?
Sure. Say you designate the diameter field as a network attribute. Then, when you run a trace, you could filter it to only analyze pipes where the diameter attribute is, say, greater than 200 millimeters.
Ah, data-driven tracing.
Exactly. Very specific analysis based on the asset's characteristics.
Very powerful. Are there other uses for network attributes?
Oh, yeah. They're crucial for containment and structural attachment rules, how things associate.
Uh-huh.
Also fundamental for generating network diagrams, those schematic views. And they can influence versioning and editing workflows, too. Make them smarter.
So they're pretty fundamental for interacting with the network data.
Absolutely. Quite central to analysis and management within the utility network.
Well, we've certainly covered a lot of ground in this deep dive. It's really clear this utility network is a highly sophisticated system. So many interconnected parts, all working together to model these complex infrastructures.
It really is. A lot of thought goes into structuring it correctly.
And understanding these elements, the structure, the rules ensuring integrity, the subnetworks for logic, terminals for connections, tiers for organization, it really gives you a solid foundation, whether you work with these systems or just want to understand them.
Well, what's particularly fascinating is how this digital representation tries to mirror the complexity and the critical dependencies of the real physical world.
Yeah.
The rules, the terminals, the tiers, they all contribute to making a more accurate, more reliable digital twin.
So maybe the next time the lights flicker briefly or your internet blip gets fixed quickly.
I'll take a moment to consider this intricate digital foundation. The utility network, the rules, subnetworks, tiers, all playing a role in delivering those services reliably. Think about the real-world impact of these digital models and how they help keep everything running. Thanks for joining us on this deep dive.